In a lab outside Beijing, a team of Chinese researchers powered up a processor that contained almost no silicon at all. It ran a full operating system. It executed instructions. It did the ordinary, boring work that a computer chip is supposed to do. And it did all of it using tiny tubes of carbon, each one about 10,000 times thinner than a human hair. The strange part was not that it worked. The strange part was that it worked at all. In a country that had been deliberately cut off from the world's most advanced chip-making machines. The tools that Western companies consider absolutely essential for building modern processors were never delivered to China. The export licenses were denied. The service contracts were canceled. The engineers who used to fly in for maintenance stopped coming. And then the announcement started anyway. What follows is a story about a technological gamble that almost nobody outside a handful of research labs took seriously 10 years ago. It involves carbon, light, physics that sounds made up, and a very specific kind of desperation that turns out to be extremely good for innovation. But before any of that makes sense, you need to understand why silicon, the material that built the modern world, is quietly running out of road. If you find this kind of deep dive interesting, hit the like button and subscribe, because these take a long time to research and put together. For about 60 years, the entire computer industry ran on a single, beautifully simple promise. Every couple of years, engineers figured out how to make transistors smaller. Smaller transistors meant more of them fit on a chip. More transistors meant more computing power. And because the manufacturing process stayed roughly the same, the price per transistor kept falling, faster and cheaper, over and over, decade after decade. That promise had a name. People called it Moore's Law, after the Intel co-founder who noticed the pattern in the 1960s. It was never actually a law of physics. It was an observation that turned into an industry-wide expectation, and then into a business plan. Entire companies, entire economies, were built on the assumption that next year's chip would be better than this year's chip. For most of that run, it worked spectacularly. Transistors went from being visible objects you could hold in your hand to structures measured in nanometers. A nanometer is 1/1,000,000th of a meter. To give you a sense of scale, a single sheet of paper is roughly 100,000 nanometers thick. Modern transistor features are a few dozen atoms across. And that is exactly where the trouble starts. When you shrink something down to a few dozen atoms wide, it stops behaving like a normal object. A transistor is basically a switch. It either lets electricity through or it blocks it. That is how computers represent ones and zeros. But at the atomic scale, electrons stop obeying the rules we expect. They start doing something called quantum tunneling, where an electron simply appears on the other side of a barrier it should not have been able to cross. Imagine building a wall to keep water in a pool, and then discovering that when the wall gets thin enough, water molecules just teleport through it. That is roughly the problem. The switch stops being a reliable switch. It leaks. And leaking transistors mean wasted power, generated heat, and errors in calculation. Chip designers have fought this with incredibly clever engineering. They changed the shape of transistors from flat structures to three-dimensional fins standing up off the surface. Then they wrapped the control gate all the way around the channel. Each redesign bought a few more years. But every generation gets harder, more expensive, and delivers smaller gains than the last one. There is another problem, and it might be worse. Making these chips requires a machine that is arguably the most complicated device humans have ever mass-produced. It is called an extreme ultraviolet lithography system, and only one company on Earth builds it. That company is ASML, based in the Netherlands. These machines cost hundreds of millions of dollars each. They work by firing a laser at droplets of molten tin about 50,000 times per second, vaporizing them into plasma that emits ultraviolet light at a wavelength of 13.5 nanometers. That light then bounces off a series of mirrors so precise that if you scaled one up to the size of Germany, the largest bump on its surface would be less than a millimeter tall. The whole system operates in a vacuum because that specific wavelength of light gets absorbed by air. Nothing about that is exaggeration. It is genuinely one of the most absurd feats of precision manufacturing in human history, and it took decades of collaboration between companies across multiple countries to build. Which brings us to the part where geopolitics enters the story. Starting in 2019 and accelerating sharply in 2022, the United States government began restricting what chip-making equipment could be sold to China. Then it pressured the Netherlands and Japan, the two other countries with critical pieces of the supply chain, to do the same. The restrictions were specific and surgical. They targeted the tools needed to make the most advanced chips, the design software used to lay them out, and eventually even the ability of American citizens to work for Chinese semiconductor firms without special permission. The logic was straightforward. Advanced chips power, artificial intelligence, missile guidance, encryption breaking, and surveillance systems. If you control the choke point, you control the pace at which a rival can develop those capabilities. And it was, by most measures, an effective policy. Chinese chip makers were locked out of the machines. Domestic manufacturing stalled at older process nodes. Companies that had been buying advanced processors from abroad suddenly could not. But there is a thing that happens when you close a door on a country with 1,400 million people, enormous state funding, and a very large population of extremely capable engineers. They do not simply stop. They start looking for a different door. And this is where the story gets genuinely interesting, because the door they went looking for was not a slightly better version of silicon. It was a way around silicon entirely. Here is the strategic insight that seems to have driven a lot of Chinese research funding over the past decade. If you are behind in a race, and the leader controls the racetrack, running faster on the same track is a losing strategy. You will always be a lap behind, using worse equipment, paying more for it. The only way to actually win is to change what the race is about. So instead of pouring everything into catching up on silicon lithography, a substantial chunk of Chinese research effort went into materials and architectures where nobody had a decisive lead yet, where the playing field was, if not level, at least not already owned by someone else. The first of those bets was carbon. Carbon nanotubes were discovered properly in the early 1990s. Picture a sheet of graphene, which is carbon atoms arranged in a flat honeycomb lattice, exactly one atom thick. Now roll that sheet into a seamless cylinder. That is a carbon nanotube. It is about 1 nanometer in diameter, which means it is naturally, inherently smaller than anything silicon lithography has ever managed to carve. And it has properties that make electrical engineers a little emotional. Electrons move through a carbon nanotube with remarkably little resistance. They can carry enormous current densities without degrading. They conduct heat better than almost anything else we know of. And critically, because the tube is already 1 atom thick in its walls, you get the electrostatic control that silicon engineers have been chasing with increasingly desperate three-dimensional structures for free. By default. On paper, a carbon nanotube transistor should be able to run roughly 10 times more energy efficient than a silicon one at the same performance level, or run considerably faster at the same power budget. Those are not marginal improvements. Those are generational leaps. So why has the entire world not switched over already? Because carbon nanotubes are, to put it politely, an absolute nightmare to work with. When you grow nanotubes, you do not get one perfect type. You get a mixture. Depending on the precise angle at which the carbon lattice rolls up, a nanotube ends up either semiconducting, which is what you want for a transistor, or metallic, which means it conducts all the time and is useless as a switch. A typical batch comes out roughly 2/3 semiconducting and 1/3 metallic. That is a disaster. A chip with billions of transistors cannot tolerate 1 in 3 being permanently stuck on. It would not compute anything. It would just be an expensive heater. There is a second problem. Even if you sort them perfectly, you then have to place them. Millions of individual tubes, each a nanometer wide, need to be laid out in parallel rows with consistent spacing, aligned in the same direction, across a surface the size of your palm. Nanotubes in solution, naturally want to clump together into tangled bundles, like a handful of spaghetti dropped in water. Getting them to lie down in neat, evenly spaced rows is a bit like trying to comb a pile of thread with a magnet. For roughly 20 years, labs around the world, including IBM, Stanford, and MIT, worked on these problems and made real but incremental progress. Purity levels crept up, alignment techniques improved, everyone published papers, nobody built a manufacturable process. Then, in 2020, a team at Peking University led by Professor Zhang Ziyong published a paper in the journal Science describing something they called dimension-limited self-alignment. The trick, in simplified terms, was this. Rather than trying to place nanotubes and then fix their arrangement, they engineered the process so that the tubes arranged themselves correctly as a consequence of the physics involved. They used a solution containing sorted, purified, semiconducting nanotubes and controlled the surface chemistry and flow conditions so that as the solution moved across the wafer, the tubes naturally lined up in the direction of flow and spaced themselves out at consistent intervals. They reported purity above 99.9999% for semiconducting tubes, and alignment across a 4-inch wafer with density in the range of 100 to 200 tubes per micrometer. Devices built from that array outperformed comparable silicon transistors in current density and transconductance. That was the moment a lot of people in the field started paying much closer attention. 4 years later, in 2024, a team at Peking University announced a working microprocessor built entirely from carbon nanotube transistors. It contained roughly 3,000 transistors, ran at a modest clock speed, and executed a reduced instruction set. By silicon standards, it was primitive. A modern smartphone chip has something in the range of 20 billion transistors. But that comparison misses the point badly. Silicon's first working integrated circuits in the early 1960s had a handful of components too. What matters is not the transistor count. What matters is whether the thing works at all, whether the manufacturing process is repeatable, and whether the yield is high enough that you can imagine scaling it. And the answer to all three, apparently, was yes. Around the same time, other Chinese groups were making noise in a completely different direction. Instead of changing the material electrons move through, they proposed changing the messenger entirely. Stop using electrons, use light. Photonic computing has been a research topic for decades, and it has a very obvious appeal. Photons travel faster than electrons move through a conductor. They generate almost no heat because they do not bump into atoms the way electrons do. And here is the part that seems almost unfair. Multiple beams of light can occupy the same physical space at the same time without interfering, as long as they are at different wavelengths. That means one waveguide can carry many independent data streams simultaneously. Electrons cannot do that. Two currents in the same wire just become one current. The catch has always been that light is terrible at some things computers need. Logic operations require one signal to control another, and photons famously do not interact with each other. That is why we do not already have optical laptops. The workarounds involve converting light to electricity and back again, and those conversions eat up all the speed advantage. But there is one category of computation where photonics is astonishingly well suited, and it happens to be the single most economically important category right now. Matrix multiplication. Artificial intelligence, at the mathematical level, is mostly enormous amounts of matrix multiplication. Take a grid of numbers, multiply it by another grid of numbers, add the results, repeat billions of times. That is what training a large language model actually consists of. It is not clever. It is just extremely repetitive arithmetic performed at an inhuman scale. And you can do matrix multiplication with light almost passively. Send beams through a carefully designed array of interferometers and phase shifters, and the interference pattern that emerges on the other side is the mathematical product. The computation happens at the speed of light propagation through a few millimeters of material, which is essentially instant, and it consumes almost no energy because you are not switching billions of transistors. In 2023 and 2024, Chinese groups at Tsinghua University published results on photonic chips designed for exactly this. One system, which the researchers named Taichi, was reported in Science as achieving energy efficiency several orders of magnitude beyond leading electronic AI accelerators for certain workloads. Another, from a Shanghai group, focused on photonic tensor cores. Now, a necessary reality check, because this is where a lot of coverage of this topic goes completely off the rails. These photonic systems are not general-purpose computers. They cannot run your operating system. They cannot browse the internet. They are specialized accelerators that do one narrow class of mathematics extremely well, and everything else not at all. They still require conventional electronics around them to load data, control the system, and read results out. The lasers and the conversion circuitry consume real power that sometimes gets left out of the headline efficiency numbers. If somebody tells you China has replaced computer chips with light, they are either confused or selling something. What is actually happening is more specific and, honestly, more interesting. A serious attempt to build the compute layer for artificial intelligence out of components that do not require the extreme ultraviolet machines China cannot buy. Because that is the real strategic point. A photonic chip's performance does not depend primarily on how small you can etch a transistor. The features in a photonic circuit are sized relative to the wavelength of the light passing through them, which is typically well over 1,000 nanometers for telecom wavelengths. You can build competitive photonic chips on manufacturing equipment from 15 years ago. Equipment China has plenty of. Read that again, because it is the whole thesis. The export controls were designed to deny access to sub-7 nanometer manufacturing. Photonics does not need sub-7 nanometer manufacturing. The lock was very carefully built for a door that this approach simply walks around. There is a third front in this, and it involves the flat sheet that carbon nanotubes are rolled from. Graphene is a single layer of carbon atoms in a hexagonal lattice. When it was isolated in 2004, it triggered an enormous wave of excitement, partly because electrons move through it at speeds far exceeding silicon. Some measurements put electron mobility more than 100 times higher. The problem, and it is a fundamental one, is that pure graphene has no bandgap. A bandgap is the energy barrier that lets a semiconductor switch cleanly between conducting and not conducting. Without one, a graphene transistor never fully turns off. It leaks constantly. You get speed, but you lose the ability to represent a zero, which is a fairly serious limitation for a binary computer. For 20 years, researchers tried every trick imaginable to open a band gap in graphene, cutting it into narrow ribbons, stacking layers at specific twist angles, chemical doping, applying electric fields. Almost all of these worked in the sense of opening a gap, and almost all of them destroyed the electron mobility that made graphene attractive in the first place. You would end up with a material that was worse than silicon at everything. In early 2024, a joint team involving Tianjin University and Georgia Tech reported a functional semiconducting graphene grown epitaxially on silicon carbide. By carefully controlling the growth process, they produced a graphene layer that bonded to the substrate in a way that opened a usable band gap while retaining mobility roughly 10 times that of silicon. That was the first credible answer to a 20-year-old problem. Whether it scales to manufacturing is genuinely unknown. But it exists now, which it did not before. So let us address the framing that gets used in a lot of coverage, that Western engineers cannot figure out how China did this. That is not really accurate, and it is worth being precise about why. Western engineers understand the physics perfectly well. The papers are published in Science and Nature. They are peer-reviewed. The methods sections describe the processes. There is no secret formula hidden in a vault in Beijing. Carbon nanotube self-alignment, photonic matrix multiplication, epitaxial graphene. These are all publicly documented approaches that researchers at Stanford, IBM, and MIT can read and, in many cases, have replicated. The gap is not in understanding, the gap is in commitment. Building a manufacturing process around a new material takes 10 to 20 years and tens of billions of dollars, and during most of that period, it produces nothing commercially viable. A publicly traded American semiconductor company cannot easily justify that to shareholders when the existing silicon roadmap still delivers improvements every 18 months and generates enormous profit today. Every dollar spent on a speculative carbon nanotube fab is a dollar not spent on the next silicon node that will definitely make money. This is not incompetence. It is the entirely rational behavior of firms operating under quarterly earnings pressure. Economists have a name for it. They call it the innovator's dilemma, and it describes how successful companies systematically underinvest in technologies that would disrupt their own profitable business. China's semiconductor push does not operate under that constraint. State-directed funding through vehicles like the National Integrated Circuit Industry Investment Fund, informally known as the Big Fund, can absorb losses for 2 decades if the strategic goal justifies it. Research at Peking University and Tsinghua does not need to show a return next quarter. And crucially, the export controls removed the alternative. When you cannot buy the silicon machines, the risky long-term bet stops looking risky. It becomes the only bet available. Pressure did what boardroom incentives could not. Now, the honest part. There are enormous reasons for skepticism here, and anybody presenting this as a finished victory is not being straight with you. First, laboratory demonstrations and mass production are separated by a canyon. A 3,000 transistor carbon nanotube processor is roughly 7 orders of magnitude away from a modern chip. Getting there requires yield, which means defect rates per billion components, not per thousand. Nobody has demonstrated that. Second, there is a complete ecosystem problem. Silicon has 60 years of accumulated tooling, design software, simulation models, standardized cell libraries, and a global workforce trained on it. A carbon nanotube industry would need all of that rebuilt from scratch. That is arguably a bigger obstacle than the physics. Third, Chinese research announcements sometimes emphasize the most favorable metrics and omit context. That is true of research announcements everywhere, including American ones. But the political incentives around technological self-sufficiency add extra pressure. Some results have been independently replicated. Others have not yet been. Fourth, and this is the one people underestimate, silicon is not standing still. Chip makers are moving to gate-all-around architectures, backside power delivery, high numerical aperture lithography, and advanced three-dimensional packaging that stacks multiple dies together. These techniques are extending the silicon roadmap further than pessimists predicted 5 years ago. The target these alternatives have to hit keeps moving. So the reasonable position is somewhere between the two loud extremes. China has not obsoleted silicon. Nobody has obsoleted silicon, and probably nobody will for a long time. But the claim that export controls would freeze Chinese capability in place has clearly not aged well either. What the controls actually did was redirect enormous resources into approaches nobody else was funding seriously. And there is a scenario worth thinking about that does not require any of this to fully replace silicon. Consider what happens if photonic accelerators become good enough for artificial intelligence workloads, specifically, not for general computing, just for training and running large models. That single application currently accounts for a rapidly growing share of global computing demand and an even larger share of the industry's profit. It is the reason certain chip companies became some of the most valuable enterprises on the planet. If a country can build competitive AI compute using photonic chips fabricated on older equipment, then the choke point stops being a choke point for the thing that matters most. The extreme ultraviolet machine remains the most sophisticated tool ever built. It just stops being the gate through which everyone must pass. That would be a genuinely significant shift in how technological power is distributed, and it would happen without a single silicon transistor becoming obsolete. There is a longer historical pattern here that is worth sitting with for a moment. Export controls do not stop capability. What they do is change the shape of the capability that eventually emerges. They make it slower, more expensive, and often architecturally different from what it would otherwise have been. Sometimes that difference is a weakness. Sometimes it turns out to be an advantage nobody anticipated. Whether the alternatives arrive fast enough to matter is the open question, and honestly, nobody knows the answer. Not the researchers, not the policymakers, and definitely not anyone confidently declaring a winner on the internet. What we can say is that the assumption underlying a lot of strategic thinking over the past decade, that computing progress is inseparable from one specific manufacturing technique controlled by a small group of allied countries, is being actively tested right now. And it is being tested by people who have every reason to prove it wrong. Think about what that processor outside Beijing actually represents. Not the transistor count, which is unimpressive, not the clock speed, which is slow. What it represents is a proof that a computer can be built from something other than the material every computer has been built from since the 1960s, using equipment that does not require permission from a foreign government to obtain. That is a small thing today, 3,000 transistors doing simple arithmetic. But silicon started small too. The first integrated circuit had a handful of components on a sliver of germanium, and the engineers who built it were told repeatedly that it would never replace vacuum tubes at scale. The manufacturing was too difficult, the yields were too poor. The ecosystem did not exist. They were correct about all of it. They were just correct for about a decade, and then they were not. The most useful way to think about this is probably not as a race with a finish line, but as a divergence. For 60 years, the entire world computed the same way, using the same material, made by the same handful of companies, using machines from one factory in the Netherlands. That was historically unusual. It was a monoculture. And monocultures are efficient right up until they are fragile. What we may be watching is that monoculture ending, not through one side defeating the other, but through the emergence of parallel approaches that are good at different things. Silicon for general computing, photonics for the enormous parallel mathematics of artificial intelligence, carbon for extremely low-power devices where energy efficiency matters more than raw speed, different tools for different jobs, developed in different places, for reasons that had as much to do with politics as with physics. That is a messier world. It is also probably a more resilient one. The engineers in that lab did not make silicon obsolete. What they did was demonstrate that the assumption of silicon's permanence was always a choice rather than a law. And once you demonstrate that, other people start asking the same question in other laboratories, and the monopoly on imagination breaks before the monopoly on manufacturing does. Maybe carbon nanotubes stall out and never scale. Maybe photonic computing remains stuck in the accelerator niche forever. Both outcomes are entirely plausible, and plenty of serious researchers expect exactly that. But the reason this story matters is not that any single one of these technologies is guaranteed to win. It is that a very large amount of money and talent is now being directed at the question of what comes after silicon, in a way that simply was not happening 5 years ago. Somebody decided the door was closed and started building a different door. Whether or not that specific door opens, the building has started. So the honest summary is this: silicon is not obsolete and will not be for a long time. China has not solved computing, but the assumption that one country could hold a permanent choke point on the most important industry of the century by controlling access to one machine is looking considerably shakier than it did when the policy was written. And the engineers who are supposedly unable to figure out how it was done can read the papers just fine. What they cannot do, at least not easily, is convince a board of directors to spend $20 billion on something that will not turn a profit until 2040. Sometimes that is the entire difference between who gets there first. If you got something out of this one, hit like and subscribe. We break down the technologies, industries, and geopolitical shifts that are quietly reshaping the world every single week, And this stuff takes serious research to put together properly. Turn on notifications so the next one actually reaches you. Now I want to hear from you. Do you think alternative materials genuinely break the silicon monopoly within the next decade, or does silicon keep winning because the ecosystem around it is simply too big to replace? Tell me in the comments, and I will read them.